வணக்கம் மாணவர்களே. 3 விஷயங்களை நம்ம இதுவரைக்கும் பார்த்தோம். நம்பர் 1, சாலிட்ஸ் அப்படின்றதனுடைய ப்ராப்பர்ட்டிஸ நம்ம என்ன பண்ணோம்னாக்க 3 டைமென்ஷனல் வியூவோட சிக்ஷா வீடியோன்ற வீடியோல பார்த்தோம். அந்த வீடியோ உங்களுக்கு என்ன தெளிவுபடுத்துனாக்க, ஒரு ரிஜிட் பாடி, சாலிட், அதாவது இன்கம்ப்ரசிபிளா இருக்கக்கூடிய, டெஃபினைட் ஷேப் இருக்கக்கூடிய, டெஃபினைட் வால்யூம் இருக்கக்கூடிய, ஹை டென்சிட்டி இருக்கக்கூடிய ஒரு கிறிஸ்டலின் சாலிட்ஸ்ல இன்டர்அட்டாமிக் டிஸ்டன்ஸ் R0 இருக்கும். அந்த R0ன்ற டிஸ்டன்ஸை மாற்ற முயல்றப்போ, அதிகரிக்கிறவோ அல்லது குறைக்கவோ முயலுகின்ற போது, எலாஸ்டிசிட்டின்ற ஒரு ப்ராப்பர்ட்டி இருக்கக்கூடிய மெட்டீரியல் தன்னுடைய ஒரிஜினல் ஷேப்பை ரீகெயின் பண்ணும். அந்த ரீகெயின் பண்ணக்கூடிய இன்டர்னல் ஃபோர்ஸுக்கு பேரு ஸ்ட்ரெஸ்ன்னு பேரு. ரீகெயின் பண்றதுக்கு முன்னாடி நம்ம கொடுத்த ஃபோர்ஸுக்கு பேரு டிஃபார்மிங் ஃபோர்ஸ்னு பேரு. டிஃபார்மிங் ஃபோர்ஸ்னால ஸ்ட்ரெயின் ஆன ஒரு பாடி இன்டர்னல் ஃபோர்ஸ்னால ரீகெயின் பண்ணிக்கக்கூடிய கெப்பாசிட்டி இருந்ததுன்னா அதுக்கு பேரு எலாஸ்டிக், இல்லைன்னா அதுக்கு பேரு பிளாஸ்டிக். ஆனா 5 கான்செப்ட் பார்த்தோம். என்னன்னா 5 கான்செப்ட் பார்த்தோம் அப்படின்னாக்க, எலாஸ்டிசிட்டின்னா என்ன, ஸ்ட்ரெஸ்னா என்ன, ஸ்ட்ரெயின்னா என்ன, ஸ்ட்ரெஸ்லயே 2 விதமான ஸ்ட்ரெஸ். ஃபோர்ஸ் நார்மலா ஆக்ட் பண்றப்போ டான்ஜென்ஷியல், அதாவது நம்ம என்ன சொன்னோம்னாக்க, நம்ம கம்ப்ரசிபிள் ஸ்ட்ரெஸ், லென்த் மாறுபடக்கூடிய, லென்த் ஸ்ட்ரெச்சான வரக்கூடிய ஸ்ட்ரெஸ். 3வது ஹைட்ராலிக் ஸ்ட்ரெஸ்ன்ற ஒரு ஸ்ட்ரெஸ்ஸை பத்தியும் நம்ம பார்த்தோம். ஸ்ட்ரெயினும் அதே மாதிரி ஷேப், சைஸ், வால்யூம். வால்யூம் மாறினா வால்யூம் ஸ்ட்ரெஸ், ஷேப் மாறுச்சுன்னா ரிஜிடிட்டி மாடுலஸ், லென்த் மாறுச்சுன்னா அதுக்கு பேரு நம்ம யங்ஸ் மாடுலஸ் சொல்றோம். யங்ஸ் மாடுலஸ், ஷியர் மாடுலஸ், பல்க் மாடுலஸ். இப்போ மெதுவா அந்த கான்செப்ட் படிக்கிறப்ப நம்ம என்ன பண்ணோம்னாக்க, 5 விதமான மெட்டீரியலை பத்தி படிச்சோம். உதாரணமா ஸ்ட்ரெஸ் ஸ்ட்ரெயின் கர்வ் அப்படின்ற ஒரு கர்வ்ல என்ன பார்த்தோம் அப்படின்னாக்க, ஸ்ட்ரெஸ் ஸ்ட்ரெயின் கர்வ் அப்படின்ற கர்வ் என்ன பண்ணுச்சு அப்படின்னாக்க, நமக்கு மிக முக்கியமான ஒரு தகவலை சொல்லுச்சு. OAன்ற பகுதி பர்ஃபெக்டா ஸ்ட்ரெஸ்ஸுக்கும் ஸ்ட்ரெயினுக்கும் டைரக்ட்லி ப்ரொபோர்ஷனல் ரிலேஷன் இருக்கும். ஹூக்ஸ் லா ஒபே பண்ணக்கூடிய எலாஸ்டிக் மெட்டீரியல், ஒண்ணுமே பிரச்சனை இல்லை. A to B ஸ்ட்ரெஸ் ஸ்ட்ரெயினுக்கு ப்ரொபோர்ஷனலா இருக்காது, ஆனா எலாஸ்டிக். Bல இருந்து விட்டீங்கன்னாக்கா அந்த மெட்டீரியல் மறுபடியும் ஒரிஜினல் பொசிஷனுக்கு வராது, கொஞ்சம் மாறுபட்டு இருக்கும். அதுக்கு பேரு பெர்மனன்ட் செட் அப்படின்னு பேரு. B to D அந்த மெட்டீரியல் வந்து பிளாஸ்டிக்கா மாறிடுது, Bல ஈல்டு பாயிண்ட் ஆயிடுது, எலாஸ்டிக் லிமிட் அங்க முடிஞ்சு போயிருது. அப்புறம் DE 2 பாயிண்ட். Dல வந்து அது என்ன ஆயிடுதுனாக்க, ஸ்ட்ரெஸ்ஸே இல்லாம ஸ்ட்ரெயின் வர்றது தெரியுது, ஈல பிரேக் ஆயிடுது. DEயும் பக்கத்துல இருந்ததுன்னா அதுக்கு பேரு பிரிட்டைல் அப்படின்னு பேரு, ஈஸியா உடையும். DEயும் தள்ளி இருந்ததுன்னா அதுக்கு பேரு நம்ம மிக முக்கியமா என்ன சொல்றோம்னாக்க டக்டைல்னு சொல்றோம். பிரிட்டைல், டக்டைல். பக்கத்துல இருந்தா பிரிட்டைல், தள்ளி இருந்தா டக்டைல். அதை தவிர ஒரு மெட்டீரியல் ஸ்ட்ரெஸ், அது டிஃபார்மிங் ஃபோர்ஸ் ஆக்ட் ஆச்சுன்னா ஸ்ட்ரெயின் ஆற மெட்டீரியல் மீண்டும் பழைய நிலைமைக்கு மெதுவா வந்ததுன்னா அது ஒரு டைப் ஆஃப் மெட்டீரியல். 2வது ஹிஸ்டெரிசிஸ், ஃபேட்டிக், இந்த மாதிரி கான்செப்டை பார்த்தோம். பிறகு ஸ்ட்ரெஸ் ஸ்ட்ரெயின் ஃபார்முலாவை எடுத்துக்கிட்டு அனலைஸ் பண்ணிட்டு ஐபீம், போன் 2 அப்ளிகேஷனை பத்தி பார்த்தோம். அப்புறம் யங்ஸ் மாடுலஸ்ல 4 வகையான ப்ராப்ளம் டைப்பை பார்த்தோம். இப்போ ஷியர் மாடுலஸ் போறோம். நல்லா கவனிச்சுக்கோங்க. ப்ராப்ளம் டைப் 16 வகையான ப்ராப்ளம்கள் கேட்க முடியும். இந்த 16 வகையும் நிதானமா எக்ஸ்பிளைன் பண்ண முயற்சி செய்வோம். தேங்க்யூ.
Here we're going to talk about shear stress and strain in our next video. So we're just going to talk about the basics and explain what that really is. Again, when we talk about stress and strain, the definition of the ratio stress divided by strain in this case is going to be equal to what we call the shear modulus So let's write that down. Shear modulus, which is the measurement of the property of a material related to the shear stress and the shear strain. We don't know yet what it is, but hang with me. Again, shear stress is force divided by area, so that hasn't changed. What do we call the shear strain? Well, to illustrate that, I have a little drawing right here. Let's say we have a big block of some sort of material. And let's say that we anchor one part of it down on the ground like here. We nail like a 2x4 down here so that this can't move. And now we go ahead and push on the material in this direction. Well, what will happen is this material will deform. And how it will deform is that this top portion of it will be pushed to the right, and because the bottom portion here cannot move, it'll stay in place. And what we find is that this will deform like this, and the material will, in a way, bend kind of like this. I'm hoping that becomes clear. My drawing skills aren't the greatest, but you can see that the top portion of the material has moved over a distance like this, and let's call this distance, let's say, call it delta x. A certain amount of deformation of the top portion of material where the bottom portion of material is not deformed at all. And of course, it does depend upon the height, h here. If this height is very small, then delta x will probably be very small as well. If h is very large, then delta x could be proportionally much larger as well. And of course, the amount that the material deforms like that will depend upon what we call the shear modulus, which is the strength of the material in this particular fashion. So therefore, the shear strain cannot be defined as, you've probably guessed it, the amount of deformation in this direction right here as a function of the height of the material. So this will be delta x divided by h. And this here is the ratio of shear stress divided by shear strain, which is defined by the strength of the material as being called the shear modulus. So we're going to call this equal to S. And that's simply the ratio of the shear, and I'll write it down again, shear stress divided by the shear strain. Now, materials that are really strong, that have a very high shear modulus, you can push on really hard and they will deform just a very small amount. Metals, for example, will probably fall in that category. And even wood, you have a big wood block and you push on it really hard this way and hold it back here, it's not going to deform very much. Now, of course, you have some other material like a soft plastic or a foam or something like that. You push on like this and it will deform quite a bit. So those have very small shear modulus. Notice that F divided by A, if that ratio is very large, so if that's a really large force divided by a small area, then you expect a large deformation. Unless, of course, the material is really strong. If the material is really strong, then it requires an enormous amount of force to cause a small deformation. So that's really a good way to look at it. Another thing that's different about the area is that the cross-sectional area is the top portion of it, is the surface on the top. And so sometimes it's really hard to visualize. So let me show you some examples where in industry, this is really an important factor. So let's say we have a steel plate that looks like this. Very large steel plate, and it's not very thick. And let's say we want to come with a big machine and cut a piece off. So let's say we have a big machine like this, and want to apply a lot of force in the downward direction and lop a piece off. So cut this little piece off like that, so we end up with a piece taken off that looks like this. Now, of course, how easy is it to do that? Well, that depends on the shear modulus of the material. If this is a very strong material, you need to apply a lot of force. But how does the delta x and the h and all that how is that taken into account? Well, notice that if you look at the other side where the material is being cut off, like so, then you can see that this here becomes the cross-sectional area of the material that's sheared. Notice that what you're going to do is, when this is still attached, you're trying to push this material away from this material, so you're going to try to stress it in this direction. So it's basically stressing it like that, and so the cross-sectional area is simply the cut-up area, or the cross-sectional area of the cut becomes the area here. So the important part of an industrial application like this is to just understand how much force will be required to go ahead and cut a piece of material off. And so what we're looking at here is the limit of that material, and that's usually defined by the maximum shear stress it can withstand. So in this case, we're looking for the shear stress max, that the material can withstand, and that's going to be equal to the ratio of the force divided by the area. In this case, the area will be the cross-sectional cut of the material, and the force is the force applied to do that. So once you know the shear stress of the material, you multiply times the cross-section area, and then you can calculate how much force you need to do that. Another application in industry where this is important, if, for example, is where you try to punch out a hole out of a material like this. Let's say you have a metal sheet, and you want to punch a hole in it. So you come with a big punch, and you come down, you apply a certain amount of force, and the question is, how much force does that require in order to punch out that material? Well, when you see the piece that was punched out, you're left with a hole. So let's draw this again over here, and then you're left with a hole, and the hole probably kind of look like this. Not quite. Let me try again. There we go. That's a little better. So that's what the hole would look like. And notice that you have a radius of the hole, and you have a circumference of the hole, where the circumference of the hole is equal to 2 pi times the radius. And then you have the height, or the thickness of that material. So it turns out, again, the area that we're interested in, the cross-sectional area that we're interested in, is simply the area left by the side of the hole. So if you say, well, this is the thickness of the material right here, let's call this T for thickness, then the area here would simply be the circumference of the hole, 2 pi r, and you multiply times the thickness T, and that now gives you the cross-sectional area of the cut, which would be kind of the same as the cross-sectional area of the cut here. And again, when you talk about the shear stress of a material, it would be the force required to punch a hole through there, when the leftover area along the sides of that hole would be equal to A, which is equal to the circumference, 2 pi r, times the thickness of the material. And so that's a good application of the shear modulus. In the next couple of videos, I'll do some examples of how we calculate the shear stress and the force required to cut or cut holes through material.
Interesting. இதுக்கும் அப்ளிகேஷன் அவர் சொல்றாரு பாருங்க. ஒரு பாடியினுடைய டைரக்ஷனுக்கு பேரலா ஒரு ஃபோர்ஸ் வரப்போ அந்த பாடியினுடைய அடிப்பரப்பு ஃபிக்ஸ் ஆயிடுச்சுன்னா மேல் பரப்புல ஒரு குறிப்பிட்ட ஆங்கிள் நகரும். அந்த tan ஆல்பான்ற ஆங்கிள் வந்து dx by x அப்படின்ற dx by h அப்படின்ற மதிப்புனால கண்டுபிடிச்சோம். அது பேர் shear strain வரையறுத்தோம். shear stress by shear strain அப்படின்றது ரிஜிடிட்டி மாடுலஸ். தமிழ்ல மிக அழகாக சொல்லுவாங்க, அதுக்கு பேரு விறைப்பு குணகம் அப்படின்னு பேரு. விறைப்பா இருக்கக்கூடிய அதை உடைக்கக்கூடியதுதான் இந்த shear மாடுலஸ். நல்லா கவனிங்க, ஒரு மரத்துண்ட ஒரு கோடாலியை வச்சு வெட்டணும்னாக்க அது அந்த மரத்தை முழுவதுமா வெட்டுறதுக்கு எவ்வளவு மேக்சிமம் ஃபோர்ஸ் வேணும் அப்படின்னா அதை shear stress சொல்லலாம். இவ்வளவு குறுக்கு வெட்டு பரப்பு கொண்ட அந்த மரத்துண்டை வெட்டுவதற்கு தேவையான கோடாலியில வரக்கூடிய ஃபோர்ஸ் என்ன? எஃப். யங்ஸ் மாடுலஸோ வயரை பிரேக் பண்ற மாதிரி கட்டையை பிரேக் பண்ணக்கூடிய ஃபோர்ஸ், கட்டையில ஒரு ஓட்டையை போடக்கூடிய ஒரு ஃபோர்ஸ், ஒரு ட்ரில்லரை வச்சு ஓட்ட போட்டோம்னா எவ்வளவு போடணும்? அந்த ஏரியா ஆஃப் கிராஸ் செக்ஷனை ட்ரில்லர்ல ஓட்ட போடப்ப 2πrt அப்படின்னு சொல்றோம். இப்போ ப்ராப்ளம் ஏரியானா கான்செப்டை படிச்சுட்டு அதுக்கு பிறகு அந்த கான்செப்டை நம்ம என்ன செய்ய போறோம் அப்படின்னாக்க மெதுவாக இந்த கான்செப்ட் நம்ம என்ன செய்ய போறோம் அப்படின்னாக்க அப்ளிகேஷனா கொண்டு வரோம். யங்ஸ் மாடுலஸ படிச்சோம், ஐபீம் போன், சியர் மாடுலஸ படிச்சோம். என்ன அப்ளிகேஷன்றது பார்க்கலாமா?
Here's our first example of how to deal with the shear stress and the shear strain. So here again we have this block of material. We anchor it at the bottom so that it can't move to the right, and then we push on the top edge of the block, and we expect a certain amount of deformation, delta x, as a function of how high this material is, and of course the shear modulus of the material, how strong the material is against deformation. So now the question is, if we apply a force of 1,000 newtons, which is roughly 200 pounds, and we have a block of iron, so we're going to, let's use iron, and here we have the shear modulus of iron, which is 7.7 times 10 to the 10 pascals. Pascals, of course, is newtons per square meter. And let's say that the height of the block is 5 centimeters, the length of the block is 20 centimeters, the width of the block is 2 centimeters. How much will we deform the block by pushing on it like that with a force of 200 pounds, roughly over 1,000 newtons? All right, so again, the formula goes as follows. Let me write over here. The shear stress, and of course you don't have to keep writing shear all the time, it just exemplifies it, it makes it easier to follow. Shear stress divided by the shear strain is equal to, now of course, stress units always are, or the formula always is, force over area, and shear stress would be, or shear strain would be delta x divided by the height, the ratio of how much it deforms divided by the height given there. All right, I'm going to rewrite this a little bit, so this can be written as F divided by A times, and again, dividing by a fraction, same as multiplying by its inverse, so times H over delta X. And of course, the ratio of the shear stress to the shear strain is equal to the shear modulus S. Now, S was given, force is given, the area can be inferred from knowing the length and the width, and H is given, so let's say we need to find delta X, the amount of deformation. So we're going to take this portion of the equation and solve it for delta X, meaning we're going to move delta X over here and the S down here, and turn the equation around, so we get delta X is equal to, we have F times H over the cross-section area, and then the S comes down here. And so we have solved this equation for delta X. Now let's plug in the numbers, see what we get. Now noticing that since that's steel, and it's a big block of steel, I don't expect delta X to be a very big number. So here we have 1,000 newtons. The height was 5 centimeters, converting that to meters, 0.05 meters, goes 100 centimeters to a meter. Cross-sectional area, we have width times length. That will give us the cross-sectional area of the material. So that would be, the width is 2 centimeters, 0.02 meters, multiplied times the length, which is 0.20 meters. So that would be the width times the length for the cross-section area. And the shear modulus for iron is given to us as 7.7 times 10 to the 10th newtons per square meter. All right, when all is said and done, we should have a ratio of, let's see here, meters, because newtons cancel out with newtons, and these meters cancel out with meters squared, so we're just simply left with meters in the numerator. So let's find out what the number is. Expected to be small. 1,000 times 0.05 divided by 0.02 divided by 0.2 and divided by 7.7 e to the 10th equals, and sure enough, 1.62 times 10 to the minus 7, that's a very tiny number. So 1.67 times 10 to the minus 7 meters. Wow, that would be less than a micrometer. That's, wow, very small. I'm going to do this again just to make sure. Equals, sure enough, that's a really tiny amount. So less than a micrometer. I would say that block, the deformation, even though it's really there, I don't think you can measure it or even see it. So you get this block of metal, push on the top, you get a very small amount of deformation. Regardless of the results, I think the illustration is pretty clear. Again, we have shear stress divided by shear strain, which is F over area. Now in this case, it's not the cross-sectional area of a cable, but it's simply the top of the material that gets deformed in that direction. Height is the thickness of the material this way. The force applied is the force applied at the very edge of the top there, and then of course the shear modulus is the modulus related to the material, and that's how you find the deformation of a material. So that's a pretty good straightforward example to understand the shear stress and strain a little bit better. And then I have a few more examples where we're simply going to cut a piece of material off, and again the result is that we have to understand the shear stress in that case. That will be on the next video.
அப்ப யங்ஸ் மாடல்ஸ் கண்டுபிடிச்ச மாதிரி F by A delta L by L கண்டுபிடிச்சதுல delta L ஓட வேல்யூ தனியா கண்டுபிடிச்சோம். அது வந்து ஒரு 10% இன்க்ரீஸ் ஆச்சுன்னா லெங்த் இன்க்ரீஸ் ஆகிறதுக்கு எவ்வளவு ஃபோர்ஸ் தரணும்ன்றத கண்டுபிடிச்சோம். பிரேக்கிங் ஸ்ட்ரெஸ் கண்டுபிடிச்சோம். இது மாதிரி யங்ஸ் மாடுலஸ் கண்டுபிடிக்கிற மாதிரியே இப்ப ஷியர் மாடுலஸ்ல டெல்டா எக்ஸ் கண்டுபிடிச்சிருக்கோம். டிஃபார்மிங் ஃபோர்ஸஸ்னால வடிவத்துல ஏற்படக்கூடிய மாற்றம் வந்து 1 மைக்ரோமீட்டரை கண்டுபிடிச்சிருக்கோம். இப்போ அடுத்த லெவலுக்கு போலாம்.
Here we're doing another example on shear stress and shear strain. In this example, we're going to show you the difference between the shear modulus and the shear stress. Okay, remember, the shear modulus, S, we use the letter S to indicate that, is an indication of how much the material resists deformation when it gets pushed in this particular manner. So when, let's say you push it on one edge and it's held on the other side, the whole thing will deform a certain amount of delta X relative to the height of the material and the size of the material, the cross-sectional area of that piece. And so the shear modulus, S, is defined as the shear stress divided by the shear strain. The equation for that is equal to the force divided by area, which of course is the definition of stress, force divided by area, same units as pressure, divided by the shear strain, which in this case is the deformation, divided by the height of the material, h. But a practical portion of that concept is the stress portion of it. For example, let's say we have a machine that feeds a big roll of sheet of metal, let's say steel. Let's say that the width of that material, or in this case, I guess I indicate as the length of the material right here, is 2.4 meters, about 8 feet, and the thickness is 2 millimeters. And let's say a big machine comes in and lops off certain sections as this roll gets fed in, it comes down and lops it. How much force is required to shear off, and that's the term we use, to shear off a piece of metal like that? So therefore, for that we need to know the shear stress. And the shear stress is defined as shear, and I misspelled that. Shear is EA like here. All right, so shear stress is defined as force divided by area. So if the shear stress of a material is given, and we want to know how much force is required, we simply have to multiply the area times the shear stress to find the force. So in this case, we know the force necessary is equal to the shear stress times the area of the cut. And the area of the cut will simply be the exposed part of the cut right here, which area would be the length times the thickness of the width. All right, so let's find out what that is for us here. The shear stress of the material we found was 4.0 times 10 to the 8 pascals, not to be confused with the shear modulus. And we multiply times the area, so it would be 2.4 meters, the length, and then the thickness is 2 millimeters, converted to meters is 0.002 meters. And so that would be the force required to cut off those pieces of metal like that. So let's find out. 4e to the 8 times 2.4 times 0.002 equals, and wow, it's 1,920,000 newtons. So 1,920,000 newtons. Now it's a 4.48 pounds per newton, so we want to convert that to pounds and newtons. If I remember right, let's see, 1 pound is 4.48 newtons, so let's divide that by 4.48 equals, so it's roughly about 428,571 pounds. So yeah, those machines need to be built pretty strong, very strong cutting blade, very strong steel, a lot of force coming down, lopping out these sheets, but we have machines like that that do exactly that kind of thing. Big rolls of steel comes along, they cut off pieces with this big machine requiring a lot of force. But there's a very nice example of how we deal with stress and strain in the practical world.
அப்போ அடுத்த ஸ்டெப் என்ன பண்றாருனாக்க shear modulus அப்படின்றது stress by strain தான். இப்போ ஒரு இரும்பு தகடை கட் பண்றதுக்கு எவ்வளவு ஸ்ட்ரெஸ் கொடுக்கணும், எவ்வளவு ஃபோர்ஸ் கொடுக்கணும் அந்த ஏரியால அப்படின்னு பார்க்கணும்னாக்க shear stress is equal to force by area, force is equal to stress, shear stress into area. அந்த ஏரியான்றது கட் பண்ணக்கூடிய பரப்பினுடைய நீளம் மற்றும் விட்த், இதை வச்சு அவர் கால்குலேட் பண்ணியிருக்காரு. எவ்வளவு ஃபோர்ஸ் வண்டி இருக்குன்னு பாருங்க. அடுத்த டைப் போலாம்.
Here we're doing another example. Welcome to Lecture Online, and here's our third example of how we deal with stress and strain in the shear sense by shearing things off. Now notice the shear modulus simply says that there's a ratio between the force applied to material and the deformation when you push it to the side. Kind of actually have a nice little textbook sitting here. It's a physics book, tends to be very big in size, but notice this is a solid material. Of course, with the pages, it doesn't make it so solid, but if we push on the force like this, notice how the book gets deformed Materials get to form like that, and that's what we talk about when we talk about the shear modulus, the amount of deformation in this direction x as a result of the height of the material and the cross-sectional area of the material. However, in industry, we tend to look at things more in terms of just the shear stress, the amount of force required to punch a hole through a sheet of material or to chop off a piece of material. So here we're going to do an example of how to punch a hole through a steel plate. Let's say the steel plate is 5 millimeters thick, and we want to punch a hole with a diameter of 4.2 centimeters, that's almost 2 inches, and how much force will be required by the punch to do so. So again, definition, shear stress is the force divided by the area. So if we want to know the force, we say force is equal to the shear stress times the area. Now the area of a cut like that, of a cut hole, is simply the area of the side of the cutout. So the area of the side of the cutout, if you think about the side, is simply a strip that goes around the cutout like that. That would be the hole right there. You have the thickness of the cutout, which is the same as the thickness of the steel, and then of course the circumference of the cutout is the circumference of the hole that you're making. So the area in this case would be equal to the circumference, 2 pi r, times the thickness, t. That would be the area. And of course, in this case, the radius of the cutout would be half the diameter. That means the radius is equal to 2.1 centimeters if the diameter twice the radius is 4.2 centimeters. All right, now next we need to go ahead and plug that in here. Since we're dealing with steel and we have the shear stress for steel, which is 4.0 times 10 to the 8 newtons per meter squared, then we multiply times the area, which would be 2 pi times the radius, and we said the radius is 2.1 centimeters, convert to meters is 0.021 meters, and of course the thickness, 5 millimeters converted to meters, remember it's 1,000 millimeters in a meter, is 0.005 meters, 5/1000 of a meter. So now we can calculate the force required to punch a hole in a steel plate like that. So it'll be 4e to the 8 times 2 times pi times 0.021 and times 0.005 equals, and that's still a formidable force of 264,000 newtons. Okay, convert that to pounds, remember, because pounds means more to some people than others, so 1 pound is equivalent to about 4.48 newtons, roughly speaking. And so if we divide that by 4.48, we get 58,900 pounds. That's quite a bit of force. So if you build a punch press like that, you want to punch holes through sheets of metal that are 5 millimeters thick, half a centimeter, that requires quite a bit of force. But that's how we calculate that, and that's how that's related to the shear stress and the shear modulus.
இப்போ shear modulusல நம்ம என்ன நினைச்சிட்டு இருந்தோம் ஆரம்பத்துல கிளாஸ் ஆரம்பிக்கிறப்போ ஒரு பொருளுடைய வடிவத்தை மாத்துறதுன்னு. இப்போ இங்க என்ன எக்ஸாம்பிள் பார்த்திருக்கோம்னாக்க ஒரு தகட கட் பண்றதுக்கு எவ்வளவு ஃபோர்ஸ் தரும், ஒரு தகடுல ஒரு ஓட்டை போடுறதுக்கு என்ன ஃபோர்ஸ் தரும் அப்படின்னு அப்ளிகேஷன்ஸ்ல டிரைவ் பண்ணியிருக்கோம். அடுத்து போலாம். இப்போ மூணாவது மாடுலஸ் போறோம், பல்க் மாடுலஸ்.
In our next video, talking about the properties of materials, we're going to talk about what we call the bulk modulus. So we'll talk about just the basics of that. The definition of the bulk modulus, we use the letter B to indicate bulk modulus, is the ratio of the bulk stress divided by the bulk strain. And remember again, stress is always defined as force divided by area, which is kind of the same as the pressure. So how much pressure you apply to a material. Now, in the case of the bulk modulus, it makes a lot of sense to talk about pressure, because here we're taking a material like this. Let's say that the dotted lines were the original volume of the material. You apply a certain amount of force on the material, and of course that force is divided over the surface area of the material, which in other words, a certain amount of pressure to the material, and you will cause the material to shrink in volume. It changes in size as far as the volume is concerned, and we call that the strain. So the definition of the bulk strain is a change in volume divided by the original volume. So this can then be defined as force divided by area divided by the change in the volume over the original volume. But we're going to place a negative sign on that because whenever we apply pressure into a material, the volume actually shrinks. So the change is a negative change. It becomes smaller, so therefore we put the negative there to make it a little bit easier to understand. So the more force you apply, or the more pressure you apply, the more you shrink the size of the volume of the material, which makes sense because, again, as you apply pressure on a material, the molecules in the material, they push back, they don't want to be any closer together, so it's a constant fight between the repulsive force of the electrons in the material and the pressure applied to the material. The more pressure, the more you squeeze the electrons closer together. It's kind of like pushing a spring together, same kind of principle. All right, now the bulk modulus that we use for that is simply how much pressure is required to achieve a certain volume change. So the greater the number, the more pressure you need, the more force per unit area you need to achieve the same volume change. So for example, for iron, you will need almost twice as much pressure than you would need for aluminum to achieve the same volume change. So iron resists the change in volume much more so, almost twice as much, as aluminum does. And then of course if you compare it to lead, then iron requires more than 3 times as much force or pressure to give the same volume change as compared to lead. Now sometimes it makes a lot of sense to talk about compressibility of a material, which is actually the inverse of the bulk modulus. So if we take the bulk modulus, take the inverse, then we get what we call the compressibility, and we'll see in just a moment what that means. So in this case, for iron, if we calculate a compressibility for iron, typically we use compressibilities for liquids, but just as a comparison, for comparison's sake, let's do it for iron. We get 7.12 times 10 to the minus 12. Of course, that would be the inverse of pascals. It's a very small number. Now, if we take a look at the compressibility, let's say, of a liquid like water or ethyl alcohol, notice that the compressibilities are much greater for water than they are for iron, and much greater for ethyl alcohol even than it is for water. The bigger the number for compressibility, the easier it becomes to compress. So that's why if you take the compressibility for lead, you would get a bigger number than you would for iron, and therefore lead is easier to compress. So that's another way to look at it. Now, can we kind of get a feel for how that change can be interpreted, or how those compressibility numbers can be interpreted? So let's take a look at the bulk stress and the bulk strain and put those into the equation for bulk modulus. So we can say that bulk modulus is equal to force over area divided by the negative of the change in the volume over the original volume. Now I'm going to rewrite this by saying that bulk modulus is equal to force divided by area times the inverse of that, which would be the original volume divided by the change in the volume. And of course we want a negative in there, so I'll just put the negative up there so we don't forget about it. Now notice that force divided by area really is pressure, so we can write that the bulk modulus is equal to negative pressure times the ratio of the initial volume divided by the change in the volume. Now, if we solve that equation for compressibility, I'm going to move over here now, give myself a little bit more room. So we can now say that the compressibility is equal to 1 over the bulk modulus. All right, so if we then take the inverse of that, notice we get negative the change in the volume in the numerator divided by the pressure and the original volume initial. So the compressibility, in a way, is a measure of how much the volume would change as a percentage, in a way, of the original volume, and also, of course, as a function of pressure. So for a given amount of pressure, we expect a certain amount of volume change. So the bigger this number, the bigger we expect the volume change to be, the more the material will be compressed. Now notice, these compressibility numbers are actually still very, very, very tiny numbers, which means these materials do not compress a lot, and you can push on a piece of metal and you're not going to see the change in the volume. And the same with water, you can push down on some water, maybe with a piston, and you're not going to see much of a volume change. The only time that you see appreciable amount of volume changes when the pressures get to be really high. And we'll show you some examples in the next videos. But hopefully at this point you get a pretty good feel for what we mean by, first of all, the bulk modulus, which is simply pressure divided by the change in volume of the original volume. In other words, if we apply a certain amount of pressure to the material, we expect a certain amount of volume change as a function of its original volume. We can see that the numbers indicate that the bigger the number for the bulk modulus, the more difficult it is to compress the material. Then we have a term called compressibility, which is the inverse of the bulk modulus, which gives us a number that if it's bigger, it means it's more compressible. If it's smaller, it's less compressible. Again, it gives us a feel for how much force is required, how much pressure required to achieve a certain amount of volume change. And when we show you some examples, this will come a lot clearer to you. But at least I want you to have a basic understanding of the bulk modulus and of the compressibility constant, and now we'll show you some examples how to actually calculate how much the volume changes when you apply a certain amount of pressure to a material.
இப்போ மூன்றாவது மாடுலஸ்க்கு வந்திருக்கோம். அதுக்கு பேர் பல்க் மாடுலஸ்னு பேரு. ஒரு பாடியை தண்ணிக்குள்ள அமுத்துறோம்னு வச்சுக்கோங்க. அந்த பாடியினுடைய வால்யூம் பிரஷர்னால சேஞ்ச் ஆகுது. தண்ணியில ஆழம் அதிகரிக்க அதிகரிக்க அழுத்தம் அதிகரிக்கும். அந்த ஆழத்துக்குள்ள அந்த பந்தை கொண்டு போறப்போ பந்து சின்னதா மாறுது. பிரஷர் மாறுறப்போ வால்யூம் சேஞ்ச் ஆகுது. அது ரெண்டுக்குள்ள ரேஷியோவை பல்க் மாடுலஸ்ன்னு சொல்றோம். பிரஷர்னால சேஞ்ச் இன் வால்யூம் டு ஒரிஜினல் வால்யூம் நடக்கிறத ஸ்ட்ரெயின் சொல்றோம். பிரஷர் பை ஸ்ட்ரெயின் இஸ் கால்டு பல்க் மாடுலஸ்ன்னு சொல்றோம். இந்த நெகட்டிவ் சைன் பிரஷர் இன்க்ரீஸ் ஆனா வால்யூம் டிக்ரீஸ் ஆகிறத ரெப்ரசென்ட் பண்ணுது. 3 மெட்டீரியலுடைய பல்க் மாடுலஸ் கொடுத்துருக்கோம். பல்க் மாடுலஸ் அதிகமா இருந்ததுனாக்க அத நம்ம அந்த பல்க் மாடுலஸ் அதிகமா இருக்கிறது எதை சொல்லுது அப்படின்னாக்க இந்த மெட்டீரியலை நம்ம சுருக்கிறது கஷ்டம்னு சொல்லுது. ரிவர்ஸ் பாருங்க, பல்க் மாடுலஸ் ரிவர்ஸுக்கு பேரு கம்ப்ரஸபிலிட்டின்னு பேரு. அயன், அலுமினியம், லெட் இது 3ல பாத்தீங்க அப்படின்னாக்க பல்க் மாடுலஸ் அயனுக்கு கூட இருக்கு, லெட்டுக்கு 4 தான் இருக்கு, அலுமினியத்துக்கு 7 இருக்கு. 4, 7, 14. லெட்டை கம்ப்ரஸ் பண்ண முடியும், அதாவது லெட்டை அதிகமா அழுத்த முடியும். அலுமினியத்தை அதை காட்டிலும் குறைவா அழுத்த முடியும், இரும்பை அழுத்த முடியாது அப்படின்றத பல்க் மாடுலஸ் சொல்லுது. இதனுடைய ரெசிப்ரோக்கல் கம்ப்ரஸபிலிட்டி இங்கேயும் 3 சொல்றோம். இரும்பை கம்ப்ரஸ் பண்றது கஷ்டம். பாருங்க, நீர், எத்தைல் ஆல்கஹால், இந்த 1110 அப்படின்னா அதிகமா கம்ப்ரஸ் ஆகும்னு சொன்னோம். நம்ம யங் மாடுலஸ்ல ஃபோம் அயன் அதிகமா கம்ப்ரஸ் ஆகுது. யங்ஸ் மாடுலஸ் கூடவா? இல்லையே. அதே மாதிரிதான் எத்தைல் ஆல்கஹால் அதிகமா கம்ப்ரஸபிலிட்டி இருந்ததுன்னா பல்க் மாடுலஸ் கம்மியா இருக்கும். இத இங்க ரிலேஷன்ஸை மாத்தி காமிச்சிருக்கோம். F by A delta V by V நாட் அப்படின்றது பல்க் மாடுலஸ். ரெசிப்ரோக்கல் போட்டு கம்ப்ரஸபிலிட்டி போடணும்னாக்க டெல்டா V by V நாட்ன்ற வால்யூம் சேஞ்ச் எஃபெக்ட் பண்ணக்கூடிய பிரஷர் compressibility தரும். The reciprocal of the pressure will give the compressibility for a unit change in volume. இதை கன்ஃபார்ம் பண்ணி சில எக்ஸாம்பிள்ஸ் போடலாம்.
In our next Welcome to Lecture Online. In our next video here gives us an example of how we use the bulk modulus. Again, the bulk modulus by definition we use the letter B is the ratio of the bulk stress divided by the bulk strain. The stress, got a spelling error here, strain, not stain. And so the stress, of course, is the ratio of the force per unit area, which is another way of saying pressure. And the bulk strain is the ratio of the change in the volume divided by the original volume. Of course, it's negative because the volume gets smaller. So negative change in the volume. So how much will, let's say, in this example, let me explain what I've just drawn on the board here. Here's the ocean. Let's say it's the Pacific Ocean. We have a ship at the surface, and we're doing an experiment. We're lowering this deep sea submersible, is what it's called, all the way down to the deepest part of the ocean, which is found off the coast of the Philippines, called the Mariana Trench. And at the very bottom of the trench, you're 11,000 meters below the surface of the water, which is about 7 miles down. So you need a very long cable in order to lower a submersible in there. And yes, they've done that. They've actually sent people down there to take a look around. Not a lot to see, of course, at that depth, pretty dark. But it was something that they had to do. Now the question is, what will be the change in the volume of a, let's say, cubic meter of water at the surface? If you take a cubic meter of water and you bring all the way to the bottom, how much will the volume of that cubic meter change? All right, for that we need, of course, a delta V, and we need the compressibility of water, which we can then turn into the bulk modulus by simply taking the inverse of that. So let's do that. Let's take the inverse of that. So we get, so the bulk modulus for water would be 2.18 times 10 to the 9th. So the bulk modulus for H2O is equal to 2.18 times 10 to the 9th pascals. So I simply took the compressibility, since of course compressibility is the inverse of the bulk modulus, that means the bulk modulus is the inverse of the compressibility. So now that we have that, and we have an equation for the bulk modulus, let's solve that for delta V. So here we go. B is equal to the force per unit area divided by the negative change in the volume over the original volume. Now I forgot my BV here. All right, there we go. Which of course can be written as B is equal to force divided by area times the inverse of this denominator, which is V sub naught over delta V. And of course we want a negative there. Which means that if we solve that for delta V, we get minus delta V is equal to the force per unit area times the original volume divided by the bulk modulus. And of course the force per unit area, since we're talking about going down into a liquid, we could talk about the pressure. We could say the change in the volume is equal to the pressure at that depth times the original volume divided by the bulk modulus. So for the original volume, we're just going to take a cubic meter of water. So what is the pressure at this great depth in the oceans? Well, it turns out that the pressure in a liquid is equal to rho g h. H, of course, being the depth in the liquid. So even though we like to use H, or sometimes we use Y, in liquids we go negative for a positive depth. So the deeper we go, the bigger H is, the greater the pressure. So we're going to plug that in there. So minus delta V is equal to the density times G times the depth. We'll call it Y instead of H. Maybe that's easier to swallow. So we go down a depth of Y into the ocean. The original volume divided by the bulk modulus. So now let's go ahead and plug in some numbers. The density of ocean water is a little bit more dense than the density of lake water. It's 1,030 kilograms per cubic meter. G, of course, 9.8 meters per second squared. Y, the depth of 11,000 meters. And the original volume is 1 cubic meter. So that was by definition. We're just going to use that. And now, of course, the bulk modulus, we just calculated. We're going to divide the whole thing by 2.18 times 10 to the 9th pascals. Notice that if I had left it in terms of compressibility, I would simply say the change in volume is this times the compressibility instead of divided by the bulk modulus, but I just want to do it like this. So now take the inverse of that again, so we get back to the compressibility, times 10,030, times 9.8, times 11,000, and times 1. So that gives us minus delta V is equal to a minus, because I put the minus over here, we get a minus 0.05 meters cubed. So if the original volume was 1 meter cubed and the change in volume was 0.05 meters cubed, which is, if you think about it, 5% of 1 cubic meter. In other words, the water has been compressed by 5% of its original volume by the time we get to the bottom of the Mariana Trench. So 1 cubic meter at the surface of the water, pushed down to the bottom, is now only 0.95 cubic meters. So the new volume is only 95% of the original volume when it was up there. And that's how we use the bulk modulus to calculate things like that. So we'll show you another example or two to get a better feel for it. But here's a very nice one.
Bulk modulus example நம்ம என்ன பண்ணிருக்கோம் அப்படினாக்க ஒரு கப்பல்ல இருந்து 1 மீட்டர் கியூப் இருக்கக்கூடிய ஒரு பாடிய மேல இருந்து கீழே நாத்திட்டு போறோம். 7 மைல் தொலைவுக்கு அல்லது 11,000 மீட்டர் கொண்டு போனா வால்யூம்ல என்ன சேஞ்ச் வரும்னு பார்த்தோம். வால்யூம் என்னன்னாக்க 0.05 மீட்டர் கியூபா குறையும். 5% வால்யூம் குறையறத பார்த்தோம். 100% இருந்தது 95% மாறும் அப்படின்றத எக்ஸாம்பிள டிரைவ் பண்ணி காமிச்சிருக்கோம். அடுத்து போலாம்.
Welcome to our lecture online, and our next example here about the bulk modulus is a really interesting one. It deals with the Earth right here. So since this picture doesn't quite look like the Earth, let me go ahead and write it down. Here's the Earth, and at the very center of the Earth we have the central core of the Earth, which is mostly made up of iron, and it's solid. It's a solid core of iron. And we've determined by the fact that the Earth has a certain amount of average density that the density of the core must be about 12 grams per cubic centimeters. which is considerably more what it normally is on the surface, because normally density of iron at the surface is about 8 grams per cubic centimeter. So there's been a 50% increase in the density of the core due to the enormous amount of pressure. So the question now is, what do you think the pressure is at the very center of the core? Well, first of all, what we want to do, because the bulk modulus is defined in terms of pressure and the change in the volume, if we have that kind of a density change, how did the volume change? And the definition of density is equal to mass divided by the volume. So we can say the original density on the surface is equal to the mass divided by the volume at the surface. And we can also say that density final at the core is equal to the mass divided by the volume final at the core. Final. And of course, if we talk about the same clump of iron that we took at the top and then we then to the center and compressed it, the mass doesn't change. The mass will be the same for both cases. So if you now find the ratio of the density, let me find the ratio of the volumes, that's better. So the volume final over the volume initial is going to be equal to the mass divided by density final, or not divide by. If I solve for volume, I get mass divided by density, that's right. Mass divided by density final divided by mass divided by density initial. Of course, the mass cancels out because it's the same mass, which is equal to the ratio of the original density divided by the final density. And of course, since the original density was about 8 grams per cubic centimeter and the final density is 12, we can see that is equal to 2/3, which means that a volume of iron at the surface brought to the center of the earth under the tremendous pressure of the weight of the earth will have been compressed to 2/3 of its original volume, which means the change in the volume is equal to 1/3, which is equal to 33%. So we have a 1/3 or 33% change in the volume when we take a clump of iron and stick it at the middle of the earth. Based upon that, should we be able to calculate the pressure required to do so? There's one more wrinkle into this problem, because at the center of the earth it's about 6,000 degrees Kelvin. And of course we have the linear expansion of materials due to that enormous amount of heat. But I just calculated and found out that even though the core is at 6,000 Kelvin, the expansion because of the temperature change is not as drastic as the pressure change that the core experiences. So we can just go ahead and ignore that for now. It was less than 1% change the way I calculated it. So this is far greater. So now let's go ahead and use the bulk modulus. The bulk modulus is equal to the ratio of the force divided by area divided by the change in the volume over the original volume, which is equal to the pressure divided by the change in the volume over the original volume. All right, so the change in the volume over the original volume is 1/3 of the original volume. So we can say then that the pressure is equal to the change in the volume over the original volume times the bulk modulus. And of course, the change in the volume would be 1/3. We have a 1/3 decrease. Of course, we don't have to put a negative there. We could simply solve for the pressure. Times the bulk modulus. The bulk modulus for iron is 14 times 10 to the 10th pascals. So now, let's go ahead and calculate that. So we have a 14 e to the 10th divided by 3 equals. That gives us 4.67. This is equal to 4.67 times 10 to the 10th pascals. So that's the pressure at the center of the earth to the enormous weight pushing down on it. Let's see here. How many atmospheres is that? If I divide that by 101,325, that's 460,000 atmospheres. 460,000 times the atmospheric pressure. So that's the pressure at the core of the earth. So that's quite a bit, and that's enough pressure to shrink down the volume of the core of the earth to what it normally would have been, to about 1 or 2/3 of the original size that it would be if there was no pressure there, or about 1/3 reduction in the volume due to the enormous pressure caused at the center of the earth. So that's kind of an interesting result, and that's how you do that using the bulk modulus.
மிக அழகா bulk modulusக்கு இரண்டாவது எக்ஸாம்பிள் போயிருக்கோம். முதல் எக்ஸாம்பிள், 1 மீட்டர் கியூப் இருக்கக்கூடிய ஒரு திரவ பரப்பை 7 மைல் தொலைவுக்கு கொண்டு போனா 5% வால்யூம் குறையுதுன்றதை டிரைவ் பண்ணி பார்த்தோம். இப்போ பூமியினுடைய மையம் இரும்புனால் ஆன ஒரு குழம்பு இரும்பு உருகுன ஒரு குழம்பா இருக்கு. அதுல இரும்ப வந்து ஒரு மையத்துல கொண்டு போனோம் அப்படின்னாக்க எவ்வளவு பிரஷர் இருக்கும், அட்மாஸ்பியரிக் பிரஷர் விட எவ்வளவு பிரஷர் அதிகம் இருக்கும், எவ்வளவு வால்யூம் குறையும் பார்த்தோம். ஒரு சர்ஃபேஸ்ல இருந்து சென்டர் கொண்டு போனா 33% வால்யூம் குறையும்ன்றதும் அட்மாஸ்பியரிக் பிரஷரை காட்டிலும் எவ்வளவு மடங்கு அதிகரிக்கும்ன்றதையும் இங்க எக்ஸாம்பிளா பார்த்தோம். கடைசி எக்ஸாம்பிள்.
Here, our next example, we're going to do something a little bit different. We're going to set up an example of where we try to calculate the bulk modules going through an experiment. Let's say we have a container that has oil in it. We have a piston here, and we apply a certain amount of force, increasing the force, until we have an increase in pressure equal to 5 times 10 to the 6 pascals. That would be about 50 atmospheres, roughly speaking. And let's say we start with an original volume of 1,000 cubic centimeters. By applying this enormous amount of pressure, we reduce the volume by 1.5 cubic centimeters. From that, we should be able to figure out the bulk modulus, and we should be able to figure out the compressibility of this particular oil. And that's typically how we do that. All right, so let's go ahead and use our equation that the bulk modulus is equal to the force per unit area divided by the change in the volume divided by the original volume. Of course, force divided by area is pressure divided by the change in the volume over the original volume. The pressure applied was 5 times 10 to the 6th pascals, and the change in the volume of the original volume is 1.5 cubic centimeters divided by original volume of 1,000 cubic centimeters. So that's the ratio of the change in the volume to the original volume. So if we go ahead and use a calculator, that gives us 5e to the 6th. That would be times 1,000 divided by 1.5. That gives us a bulk modulus of 3.33 times 10 to the, and did I see 9? Yes, 9. And of course, what are the units? This is unitless because cubic centimeters cancel out, so it leaves us with pascals. So how does it compare to what we have here? Well, for water, we had 2.18 times 10 to the 9. Here we have 3.33 times 10 to the 9. So it's a little bit higher number than water, which would mean that this oil would be less compressible than water because it has a higher bulk modulus, more pressure required for the same volume change. The compressibility, K, is equal to 1 over the bulk modulus. That would be 1 over the number we just got, 3.33 times 10 to the 9th pascals. So if we take the inverse of this number, we get 3 times 10 to the minus 10. So that's 3 times 10 to the minus 10, 1 over pascals, or giving it the same kind of exponent, that would be 300 times 10 to the minus 10 pascals, or 1 over pascals, and that would then be the compressibility, which means the bigger that number, the easier, oh yes, that's right. Yeah, I need to convert that. So the bigger that number, the easier it is to compress the material, so it slips right in here, a little bit less compressible than water, far less compressible than ethyl alcohol, but much more compressible than iron, as an example. So here's a simple example to show you how to calculate the bulk modulus or the compressibility of a material.
Thank you. ஆகவே bulk modulus உடைய மூன்றாவது மிக எளிமையான ஒரு எக்ஸாம்பிளையும் பார்த்தோம். இதுதான் நம்ம சொல்லக்கூடிய சாலிட்ஸ்ல இருக்கக்கூடிய ஒரு ப்ராப்ளம் டைப். இது தவிர பாய்ச்சன் ரேஷியோ மற்றதெல்லாம் இருக்கு. அதை NCERT ப்ராப்ளம்ஸ் பார்க்குறப்ப பார்க்கலாம். இப்போ முதல்ல தியரி பார்க்குறோம். தியரி பார்த்ததுக்கு அப்புறம் ப்ராப்ளம் டைப்ஸ் பார்க்குறோம். ப்ராப்ளம் டைப்புக்கு எக்ஸாம்பிளும் அப்ளிகேஷனும் பார்க்குறோம். அப்ளிகேஷன் பார்த்ததுக்கு அப்புறம் NCERT ப்ராப்ளம் போடுறோம். சாப்டர் முடிஞ்சிடும். ஒரு நாளைக்கு ஒரு சாப்டர் வீதம் படிக்கலாம். மீண்டும் சந்திக்கலாம் NCERT ப்ராப்ளங்களோட. வாழ்த்துக்கள்.